Really?
Okay, welcome.
I see.
Let's get started. For homework number 4, which is available right now on Blackboard, I wanted to clarify that the turtle is 3,500 kilograms. Big turtle. Really big turtle. So it's 3.5 metric tons, not 350 kilograms. I had to make the turtle bigger, otherwise the barrel that it's floating on wouldn't be submerged far enough. So I had to change that problem. So if you already printed out the assignment, add an extra 0 to how heavy the turtle is. I've updated the PDF on Blackboard, so if you haven't got started yet, number 1, shame on you. But number 2, no need to change the PDF. All right. So that's homework number 4. It's due on Tuesday. Then a week from today, we're going to have our first exam. The equation sheet's already on Blackboard if you'd like to begin familiarizing yourself with the layout and where the equations are, and if you think anything's missing that you want to commit to memory. I don't think so. There's nothing that I intentionally left off. But have a look in advance in any case. And I already talked about the other details about exam 1. Today we're going to do just a practice problem to reinforce the curved surface calculations. So we'll do one last problem related to hydrostatic forces on curved surfaces, and then we're going to move on and talk about buoyancy. So are there any questions related to the announcements before we begin? All right, so here's the handout problem. This is similar to the shape that we looked at before, where we have a curved plate holding back water. In this one, you don't have to find the location of the vertical forces. We want to know the magnitude and the location of the horizontal hydrostatic forces. But for vertical, all you need to do is find the magnitude.
No, I got 4.5. Yeah, right. Yeah, so you do 16 miles. Oh, I haven't done that yet. Okay. That's why. That's why. Okay, you get 25.
Okay, we call it a hydrostatic force even when the fluid isn't water. You know, hydro, water, but in this case it's an oil of some sort, presumably based on the density. We still call it hydrostatic forces though, because you know, whatever the fluid is, it's not moving. It's just stationary in a tank, and so the pressure elevation relationship is pretty easy to characterize. The first thing we have to think about, what does the projection look like? And so to find the horizontal magnitude, we're dealing with a vertical projection. And the vertical projection, the projected shape in a vertical plane, is just going to be a rectangle that's 2 meters tall and 4 meters wide. Okay, so we can identify the depth to the centroid, 4.7 meters. The area of the projection, even though I wrote 9810 here, I used the correct, I guess, let me type that in. That was just a mistake in what I wrote, but the calculations are all right. This was, I used 7308 newtons per cubic meter. All right. So that's the horizontal magnitude. The location of the force, we calculate the y bar for that is the same as delta H because it's vertically oriented. The projection is. area moment of inertia will only be correct if you remember that it's the vertical dimension that you cube. So 4, the width of it isn't cubed. You just take that to the first power. So overall we have the area moment of inertia, put it into the YCP equation. And so what YCP represents in this case is just the vertical distance from the surface to the point of force application. Because it's a vertical projection, then that means that YCP doesn't have to follow an inclined path. It's just straight up from where the force is located to the surface. Any questions so far? Finally, the vertical force. Now, I broke this up. I just did a little dashed lines here to kind of delineate what the shape looks like. There's two pieces. There's this one piece that is 2 meters by 4 meters by 3.7. So that's piece 1. And then to calculate the volume of piece 2, I said there's a rectangle that's 2 by 2 by 4, and I'm going to subtract out the quarter circle element there. So 2 by 2 by 4, subtracting out the quarter circle, which is also 4 meters of width. So we have the overall volume of that smaller element up above. So here's the volume 1 and the weight of the water associated with that. Volume 2, and then multiply, oh, it's not water, oil. Shouldn't have said water. Then element 2 multiplied by the unit weight of that fluid. So the sum force, 241 kilonewtons. So that's the magnitude of the vertical force. Any questions about this example problem? All right. Well, if not, let's talk about what's going on in this picture. It's been some years since I dug up this photo, but if I remember correctly, it was taken at a filling station somewhere in Charleston. And from time to time, people tell me, oh yeah, I know where that is, but anybody know where this is in Charleston? All right, well that's not the relevant thing. What's that? Oh, I don't know. I hardly ever go to Charleston. I was hoping you'd know. So there's some fluid mechanics going on in this picture. You don't see the fluid because it's beneath the ground. The fluid in this case is groundwater. And the groundwater table elevation varies depending on if it's been dry, like recently. The groundwater elevation is probably a little bit lower because it hasn't been recharged by seepage from creeks. Because there's been a lot of dry, warm weather, the plants are continuing to draw moisture out of the soil, but it hasn't been replenished due to infiltration of rainwater. So this is a photo not during a period of drought, but after a period of really wet weather, where what happened was it was the perfect combination of wet weather, which brought the water table up. Simultaneously, this tank was empty. And so what happened was there was a buoyant force acting on the tank. Here's some other views of it. It's almost as though it was like a submarine that emerged from underground, and it had enough buoyant force that it cracked right through this relatively thick concrete. So what we're going to be talking about today is the method that we use to understand how big those buoyant forces are going to be. In other words, how can we prevent a situation like this where tanks suddenly start emerging out of the ground? It just seems like a random thing, but there was a fluid underground pushing this tank up through the concrete. So let's take a look at another cylindrical shape that can float. Better pause this recording. So right now the submarine is still in the process of surfacing. So as long as that submarine is moving, it means it's not in equilibrium yet. So it's coming up, it's still moving, it's not in equilibrium. Finally it stops and it's floating at the surface. So it's no longer coming upward. So that tells us now it is in equilibrium. So if you think about what are the forces involved here on this submarine, the two main forces is that it has weight, which is acting downward, and it has buoyant forces that are acting upward. And when they're in equilibrium, then it's not going to sink, it's not going to continue to rise, it's just going to float stably in the water. And that's what's happening once it finally comes to the surface. But whoever's controlling this submarine, if they wanted to, they could make it go back down again. So how do they do that? How do they make it so that suddenly the buoyant forces are less than the weight of the submarine? Yeah?
They bring drawing water into the outer wall.
That's right. Yeah, they suck water into the submarine. And so, there's two things. There's the buoyant force, F sub B, versus the weight of the submarine. Now, when they're at the surface, just floating there, the captain of the submarine, he can't change the buoyant, or she, can't change the buoyant force, trying not to, assume. Can't change the buoyant force, but the captain can change the weight of the submarine by drawing on ballast, as it's called, sucking in more water to tanks inside the submarine. And so we're going to focus mostly on how do you know what the buoyant force is. All right, the key item, the way to calculate the buoyant force is to understand what is the volume of water that's being displaced. So being displaced, what's the volume of water displaced, and then what's its weight? And so right now, that submarine is floating in the ocean. And by virtue of the fact that it's in the ocean, like the water that would normally be in that same location got pushed out of the way by the submarine. And that's the key idea to understanding the buoyancy that the submarine is experiencing, is the magnitude of the buoyant force is equal to the weight of the water that the submarine pushed out of the way. So when the submarine starts sucking water in, some of that water that initially it had pushed out of the way now gets to take up the same volume that previously was being displaced. And so that's what increases the weight and makes it greater than the buoyant force. So we're going to get into all of those details today. Okay, so your textbook shows this figure, and it suggests that you think about the distribution in pressure that's acting. And this is an irregularly shaped object, just to make the point that we don't necessarily have to integrate the difference in pressures between the pressures on the top and the pressures on the bottom, although we can. But just think about, if you have the bottom side of this irregularly shaped object, the pressure magnitude is going to be larger than the magnitude of the pressure on the top. And because of the fact that it's submerged more deeply, it's deeper down in the water, so the pressure is greater. So that means that the difference between the pressures acting from above and the pressures acting from beneath is such that it would cause it to float up to the surface, depending on the weight of the object. So the way that we think about the external forces that are acting on the object, in the vertical plane is going to be the differences between the pressures that are pushing it up. And so the forces that would be pushing it up is going to be the volume of the body itself and the volume of the water that's above it. Those would be how you'd calculate the magnitude of the upward forces, and the downward forces are just related to the weight of the water that's above it. And so the magnitude of the force is equal to the weight of the water, so the difference between the two, the buoyant force, the difference between the up and the down forces, is just going to be the unit weight of the fluid. It's not the unit weight of the object. And the object itself does have a unit weight. It's made out of something, whether it's made out of granite or made out of plastic. Whatever this material is, we could express its unit weight in terms of the newtons of weight per cubic meter of its volume. But the gamma that we're talking about here for the buoyant force doesn't depend on what it's made out of. Whether this is made out of plastic or rock, the buoyant forces are only related to how much water gets pushed out of the way, whatever the fluid is, in this case water. So what determines if it floats or if it sinks? It's the buoyant force compared to the weight. So let's look at this example. Let's say, for instance, that we have some plastic cube that's very, very light. It has a negligible weight, and so we just want to compare the forces that are on the bottom of it, the forces that are on the top of it, and prove to ourselves that we don't have to always calculate the difference between those forces, that it's okay for us just to rely on the idea that the buoyant force is the weight of the water and the weight of the water displaced. Okay, so first of all, part A, if we want to know the force on the top surface, we need to know the force, part A, force on the bottom. So F bottom is going to be the pressure at some depth multiplied by the area. So the depth that we're talking about, delta H times gamma, will give us the pressure, and then we're going to multiply it by that bottom area of a 1 by 1 cube. So it's oriented such that it's completely flat on the bottom and the force is acting straight up on that. So the delta H is 4 meters. That's how deep that bottom is. 9810, since we've just got water in this one. And then the area is a 1 by 1, so 1 square meter. So the force on the bottom is 39,240 newtons, and that's acting upward. And part B, if we're going to now look at what's the force acting on the top, just by calculating the pressure and the area over which that pressure is exerted. So F top is delta H times gamma times A. And again, the delta H times gamma is where we're getting the pressure at some depth. Okay, so the delta H for the top surface is 3 meters. The unit weight, 9810 newtons per meter cubed. And 1 square meter of area gives us a downward force of 29,430 newtons. So as we would expect, the forces that are acting on the bottom side of it, pushing this cube up, are larger than the forces that are pushing down on it from above. So the net difference, part C, the force at the bottom minus the force at the top, if we just find the difference between the two, it's 9810 newtons. And of course that's a familiar number because this is a 1 cubic meter box. And so now if we look at it the other way, just by calculating the F sub B, the buoyant force, it's the unit weight of the fluid that's being displaced by the box, multiplied by, in this case since it's fully submerged, the volume of the box itself. More generally, you'd only consider the submerged volume, or the volume of water that's being displaced. So, like if this box was floating at the surface and it wasn't fully submerged, you wouldn't use its whole volume. You'd only use the volume that's beneath the water line. All right, so but this one is fully submerged, so 9810 newtons per meter cubed. 1 cubic meter is the volume, so calculated the other way, we still get 9810 newtons. All right, so that's a pretty simple illustration, but it's just kind of a proof that whether you're looking at pressure acting over an area or you're considering the volume method, then you can find out what the buoyant force is either approach. So the key idea is the volume of water displaced and its weight will tell you the magnitude of the buoyant force. So here's what I was saying about an object that's not floating completely submerged. Its overall volume is described by points A, B, C, D. So its submerged volume is what we would use to calculate the buoyant force. Now, if you were told the density of that object, let's say it's like a piece of wood. So maybe in a problem like this, you'd be given the density of the wood and then the overall volume. You'd use that to find the weight. So the weight comes from the overall volume. The buoyancy only comes from the submerged volume. So that's the difference. You need to know both the weight and the buoyant force in an equilibrium, but the buoyant force comes from the submerged volume. The weight comes from the overall volume of the object. Even the volume that's above the waterline is contributing to the weight. So here's just one of those examples. What I'd like you to do is consider this plastic block, and from the dimension drawing and the description here, you can see that it's partially submerged. And based on the way that it's floating, we can answer a lot of questions about that block. We can figure out what's the buoyant force. We can figure out the weight of the block by doing a force balance. It's in equilibrium. It's floating in the water in a stable equilibrium. It's not continuing to rise, and it's not in the process of sinking. It's stable. So go through this steps 1 through 5, because ultimately the way that it's floating will tell us what is the specific weight of the block and what's the specific gravity of the block. This is a way that we can figure out how dense something is by considering how it floats in the water. That's with ships what they do. They can figure out how much cargo a ship has on board by how it floats. There's all these numbers that are written on the side of ships. And so they can know how much grain is on board specifically by how deeply the ship is sitting in the water. In this case, it's not a ship, it's just a block. So go through steps 1 through 5. Ultimately, what we're after is finding out the specific gravity. Okay, I wrote some rules of thumb on the board here. First of all, when an object is floating in equilibrium, the weight equals the buoyant force. You can bank that. That's always true. Also, always true, the buoyant force depends on the submerged volume, but the weight of an object depends on the total volume. It's not like the object itself weighs less depending on how it's submerged in water. Its weight only depends on the mass of the object and gravity. And so the mass of the object isn't changing if you submerge it or if it's totally dry. The mass of the object stays the same. So it's the total volume that applies for calculating the weight of the object. Okay, so we've got this block with a buoyant force of 4.5 meganewtons. This is a really large block of plastic. The floating in equilibrium, so the weight and the buoyant force is the same. The volume of the block, 5 by 10 by 10. Specific weight, so we know that the weight is the volume times the unit weight, or specific weight of the block. So 9025 newtons per cubic meter for the specific weight of the block, and then specific gravity is just relative to the specific gravity of water. And lo and behold, it's not a coincidence that it's 92% submerged. The fact that this block is 92% submerged is directly related to the ratio between the specific weight of the block and the specific weight of water. So if you have an object that has a density of half of that of water, half of it will be submerged and half of it will float above the waterline. So the lighter the object is, the less of it will be submerged, because you don't need so much water displaced in order to support the weight of the object. Any questions about this example?
Can you use that factor, a little quick cut, like if you're solving for specific gravity again?
Yeah.
See how much it's submerged?
Yep, you can. So his question is, can you just look at how something is submerged and then use that to know what's the specific gravity of an object? And the answer is yes. So what's the application of that? An iceberg. So you can know the density or the specific weight of an iceberg by knowing what volume of it is up out of the water and what volume is beneath the water. Now, surveying the volume of an iceberg beneath the waterline is probably going to be tricky. So maybe the easier thing that we could say is that, we know the density of ice. That's something you can look up out of a properties table. So if you know the volume that is up out of the water, then looking at the ratio between the density of ice and the density of water will tell you then how much of it is below the waterline. I think it's something like 1/7 will be above the waterline, 6/7 will be below the waterline. All right, great question. Are there any other questions about this example? Let's do one more. Do we have time for one more?
We got 15 minutes.
No, that's time for one more. All right. We have a metal object that is fully submerged, and it's attached to a block with a cable that has negligible mass. But what we want to know is, what's the tension in this cable? That's the question that they're asking. Maybe they're worried that it may not have enough strength based on the tension, but we just want to find the tension in the cable. So we're going to have to do actually a series of force balances. We're going to have to do a force balance, first of all, on this wooden block that's up at the surface. And then we're going to have to do a force balance on the submerged metal object in order to find the tension in the cable. So here's some of the given information. First of all, this block is 10 millimeters by 50 millimeters wide and 50 millimeters into the page. And then the specific gravity of the block is given, so you can use that relative to water to find the unit weight of the wooden block. So we know that it's more submerged than it ordinarily would be. If the specific gravity is 0.3, if it wasn't connected to anything else, then it would be 3 millimeters out of 10 that it's submerged. But right now, it's submerged 7.5 millimeters out of 10. So it's more fully submerged than it normally would be because of this extra weight dragging it down. So what we can do is we can say we know what it ought to be submerged at and what it is submerged at, and the difference between the two is going to be that force that's pulling up on that metal object. And so we know the object of the metal, we know the volume of the metal object, but we don't know its density, we don't know its specific weight, but we can calculate it through following these steps. So what I'm suggesting is, first of all, since we know the submerged volume of the block and the submerged volume of the metal object, let's find the buoyant forces that are acting on both. And then go through the process of a force balance on object 1 in order to work towards understanding what is the tension in the cable that connects them. All right, we're running low on time, so what I'm going to do is I'm going to put the solution up and I'm going to talk you through what's the process for determining in the end what is the mass of that object. This is indirectly, this is a way of, we're using this whole system as a scale to find out what's the weight. All right, so the first thing we got to do is find the buoyant force on both of the objects. And the buoyant force depends only on the submerged volume. So I'm calling it buoyant force 1 and buoyant force 2. Buoyant force 1 is based on the fact that it's submerged 7.5 millimeters out of the 10. Buoyant force 2, we just use the given submerged volume. And you'll notice I converted from cubic millimeters into cubic meters. So that conversion's here on the whiteboard. Okay, so I know both of the buoyant forces directly based on the submerged volume. Now the weight of object 1, we can't say that the weight of object 1 is just equal to the buoyant force. That only works if nothing else is pulling it down. Because remember, the buoyant force that object 1 is experiencing doesn't depend only on its own weight. It's also depending on the weight of that metal piece that's beneath it. So the weight of object 1, instead, we're going to calculate with the specific gravity. So the volume of the overall object can be calculated, and the block's specific weight can be known from its specific gravity. So this block's made out of a wood that has a unit weight of 2943 newtons per meter cubed. And then finally we calculate the weight of the block by its overall volume, including what's above and beneath the water line, and then the unit weight of the block. All right, so we now know enough about that wooden block to do this force balance, to calculate the tension. So we have the weight that's acting down. The cable is pulling the block down into the water, so T represents the tension in the cable, and the buoyant force is the only thing pushing up. So we can use that to calculate the tension in the cable. It's the difference between the weight of the block and the buoyant force that it's experiencing. Usually they'd be the same if it was just floating without any interference, but there's this extra force pulling the block down. And so that extra force pulling the block down, that tension that we've calculated, now is what we can use to find out what's the weight of object number 2. Because object number 2, you can see in the force balance, is the difference between the tension, the buoyant force, and the weight. So the buoyant force we previously calculated, the tension we already knew from the previous step. The only difference is now the weight is known. And so finally from that we can calculate the mass of the object, because if we know its weight, then we just rearrange to solve for the mass as weight divided by g. All right, so I'm going to leave this up for a few minutes in case you need to copy a few things down. That's all the time we have for today. So I'll see you in class next week on Tuesday.